How nuclear fission works. Nuclear reactors generate electricity using a process called nuclear fission. Nuclear fission occurs when the nucleus of a heavy atom absorbs a neutron and becomes unstable. The nucleus then splits into two smaller nuclei called fission products. In our reaction, we use uranium-235, a common unstable atom used in nuclear fission that is forced to accept a lone neutron. We'll get into where he came from later. Uranium-235 then accepts the neutron, causing it to become overly unstable and split into krypton-92 and barium-141, and release three neutrons. This is because the reaction must remain balanced on both sides, and the neutron amount in krypton and barium does not add up to match the neutron count on uranium, causing there to be three neutrons that are released in the equation and then fly off to cause other chain reactions throughout the nuclear fission. Now about that poor lone electron. His name is Nimijutron, and no relation to Jimmy. Created as a lab experiment gone wrong, the neutron despises the friendship of the uranium atom. Jealous of their friendship, he was born from radioactive decay, as his mother, Californium-252, died bringing him into this world, and left him a pitiful, wrecked mess. The electrons of uranium were always quite distant from the group. He even started making a blog cataloging their time together. It didn't get much traction because, well, the spinning made people sick, so you probably won't see much of him.
One.
The great friends of electrons, protons, and neutrons are all hanging out and having a lovely time. They had passion and love for one another, or as the nerds call it, their binding energy. Albeit quite weak, they swam together through the water and sing and spend all their time together, frolicking out in the water and exploring together and with not a care in the world.
Well. What do we have here? A geek. A nerd.
Hey, it's Nimijutron!
Seeing everyone else get along set an uncontrollable fire in Nimijutron's heart, and he couldn't hold it back any longer. He hurled himself at the friends, tearing them apart, relishing their screams, laughing at their pain.
No, Papa, no.
Jimmy's anger didn't stop at the original group. His incredible resentment for all uranium molecules alike spread into the hearts of all the other neutrons. They all kept attacking and destroying friend groups, forcing everyone to be divided in a horrific and terrible manner. They'd attack again and again and again, non-stop. But what does this all mean in the context of a nuclear reactor? Well, when all of this happens, three main things are released. 1, a large amount of energy. 2 or 3 neutrons to start the chain reaction. And 3, a ton of gamma radiation. The neutrons, as I said, released from the reaction can strike other nuclei and cause them to split as well. This creates a chain reaction. In a nuclear reactor, this chain reaction is carefully controlled using control rods, which absorbs some of the neutrons. This keeps the reaction steady, so energy is released gradually rather than all at once. Most of the energy from fission appears as kinetic energy of the fission fragments, which quickly turns into heat inside the reactor core. That heat is used to boil water, produce steam, spin a turbine, and generate electricity. Many real power plants use these fission reactions. For example, the Palo Verde Nuclear Generating Station in Arizona is the largest nuclear power plant in the United States. Its reactors use enriched uranium fuel in a pressurized water reactor designed to generate electricity for millions of people. Another example is the 3 Mile Island Nuclear Generating Station, which also used uranium-235 fission in a pressurized water reactor to produce electricity. Most modern power plants around the world use light water reactors, where ordinary water acts both as a coolant and as a neutron moderator to slow down the neutrons and maintain the chain reaction so that they don't just fly past. The whole reason any of this creates energy has to deal with binding energy. This idea is illustrated behind the nuclear binding energy curve, sometimes called the stability curve. This curve plots binding energy per nucleon against atomic mass number. The curve reaches its maximum around elements near iron 56, which are the most stable nuclei. Elements lighter than iron tend to release energy through fusion. Elements heavier than iron tend to release energy through fission. Because uranium and plutonium are much heavier than iron, splitting them moves the resulting nuclei closer to the peak of the stability curve. This transition to a more stable configuration releases energy. On this page, we're calculating the amount of energy released from a singular nuclear fission reaction using Einstein's equation E equals mc squared. The key idea is that a tiny amount of mass disappears during the reaction, and that lost mass is converted into energy. First, we write the nuclear reaction we're analyzing. One neutron collides with the uranium-235 nucleus. This makes the nucleus unstable and splits it into two smaller nuclei, barium-141 and krypton-92, along with 3 additional neutrons. So the reaction is a neutron, uranium-235, breaks apart into barium-141, krypton-92, and 3 neutrons, and then a ton of energy. The energy release comes from a small difference in the mass between the reactants and products. This is the mass defect. To calculate the energy released, we use Einstein's equation, E equals delta m times c squared. Next, we calculate the total mass of the reactants. The reactants are uranium-235 and 1 neutron. This total mass ends up being 236.052595 atomic mass units. Next, we calculate the total mass of the products, with barium-141, krypton-92, and 3 neutrons. Add it all together, we get 235.866565 atomic mass units. Now we subtract these to find the mass defect. This gives us a 0.186 atomic mass unit difference. To convert this mass into energy, we use a common nuclear physics conversion factor. That is, 1 atomic mass unit is equal to 931.5 megaelectron volts divided by c squared. So, doing this, we get 173 megaelectron volts. This is the total energy released in a single fission reaction. That might not seem like much energy, but in a nuclear reactor, trillions of atoms undergo fission every second. So the total energy produced becomes extremely large. This energy becomes heat, which is used to produce steam, spin turbines, and generate electricity. Thank you so much to Sam Wilson, Anthony Thew, James Palmer, and Ian Morrow for your contributions to this project. Thank you.